Welcome to creating a scalable and destructible world in Hitman 2. The image you can see comes from a tech demo that's down on the show floor at the expo booth. So that's where you can go see that later if you want to. So with that plug out of the way, I'll do the housekeeping. Make sure your phones are turned to silent because we are recording the session. And we'll do a prize draw apparently at the end. Okay. Let's see if this thing works. Hey, introductions. I'm Lee Davis. I've been at Intel for quite a few years now. The photo was taken before my kids sent me grey. I used to work in games dev before joining Intel. Last year I gave a talk at GDC about mass occlusion culling, hence the picture. And with me we've got James. Let's see if his mic works.
Hello, can you hear me? Yep, I'm James Vango Brown. I work for IO Interactive. I'm a senior gameplay engineer there, so I'm going to be talking to you about the physics and the destruction system that we've been building for Hitman 2. But back to Lee.
Okay, so today's agenda. Basically, I'm doing the first part. I'll do the introduction to Hitman, the work that's already been done in the game as it stands today, looking at how we made it scale across high-end PCs, diving into a little bit about using the parallelism to enhance the crowd, the rendering, and the audio. Then I'll hand back to James. As the physics programmer, he's going to do the deep dive on the system that's implemented in Hitman and some of the stuff they're working on for the future. So let's do the introduction to the game. How many people know Hitman? Most. Great. I still can't see anyone out there because of those lights. Right, okay. For anyone who doesn't know Hitman, just a basic background. It's a third-person stealth video game. So the gameplay isn't, you're not looking first-person shooter sort of characteristics. It's very much about exploring the world and finding different ways to carry out your missions. The levels themselves are very varied, everything from cities to jungles, and as you'll see on some of the video footage, like a Miami racetrack. And that has its own set of unique challenges, as they can't make assumptions about how the levels are designed. So the first thing is well, why are Intel talking about Hitman? Why was it a good fit for the CPU? Two things. Hitman, even before we started working on Hitman 2, it's a very well-threaded engine. The image comes from their in-house micro-profiler. I think the code's actually on GitHub. So it shows you just how well-threaded it already is. And unless you've been living under a rock for the last few years, you'll have noticed that CPUs have gone from 4 cores to 6 to 8, and suddenly that task manager view is actually quite common on the home PCs. So it was a good fit all around. So what types of things were we looking at inside of the game? What fitted well with what the game designers wanted to do, and Intel's objective to scale on the CPU? So the first one, creating larger living levels. Obviously, one of the things they wanted to do was increase the size of the levels compared to Hitman Season 1. They wanted larger draw distance, much more complex environments. They also added this picture-in-picture, which you'll see in a little bit. And that has implications for gameplay design. The idea here was, if you set up a trap, a booby trap somewhere in the level, and that goes off, it will show you what happened at the booby trap, no matter where Agent 47 happens to be. So it effectively means they have to be able to render the world twice. That means the rendering itself needs to scale well. In addition to that, one of the goals was to make the crowd an even more integral part of the experience. It always has been an important part of the Hitman franchise, but they wanted to reach the point where the Agent 47 can actually blend in with the crowd and actually hide in them as part of the actual gameplay. So that meant the crowd itself, they could look at ways of scaling that on the AI and the animation systems. And finally, the tagline for Hitman 2 was make the world your weapon. So that comes down to the physics that James will be talking about. And it's an important thing to realize that the game designers see Hitman very much as a sandbox. They want people to come back and replay the game and look for different ways to achieve their mission ends. So many of these things that we're discussing, they're not there just for that one time through the game, like visual experience that's been scripted. It's things that you explore and find on your own as you go through. I'll do a little video which highlights some of them. We'll see how well it plays. You can see the picture-in-picture in the top corner. You can also see how important the crowd is and how they react to whatever Hitman has done. It's not a scripted event, it's the AI driving the actual panic that's going on. And you can see you get a very nice cinematic experience where Hitman's doing his own usual blend into the background animation and read the newspaper. And it sort of sets off quite nicely against the chaos around him. I quite like the video. I think a few people here do as well. Good. Right, one thing I did want to touch on. How many people have ever heard of the Uncanny Valley? A few. Actually, quite a few. Not too bad. It's something I came across nearly 10 years ago now, and it was a talk by another game developer at a conference down in Germany. They were talking about animation. The basic idea is originally it had nothing to do with games. It was a Japanese professor. I'll probably not get his name exactly right, but Masahiro Morei, who was doing research into human interaction with androids. And he noticed a couple of things. You start off with a very basic robot, no human attachment to it. You start making it more lifelike, and suddenly you get something like that. Now, as soon as I showed that picture to my family, my daughter and my wife, they both went, "Ah." And it's like, yeah, I can relate to that, that's good. And the assumption people had is you make them more lifelike, and that interaction increases. You start to like them more and more. But what the professor noticed was, you reach a certain point where you get something like this. They referred to the Uncanny Valley. And suddenly people felt uneasy when viewing the robots. Basically, you reach a certain point where rather than picking up the actual things that are right, you start noticing the things that are wrong. And that was the talk that someone gave many years ago about animation. They'd improved the rendering. I think it was actually a Crytek talk. They'd improved the rendering, and then they realized they were noticing the faults in their animation. Because suddenly it's like, yeah, we've got fantastic shadows, but now the feet don't match where the shadow is on the floor. And it got me thinking, and so much of what was done in Hitman was around that idea of improving the whole realism, not just rendering the pixels. One other interesting thing, and it relates to why we pushed on the crowd so heavily. This unnatural feeling you get, it's much more pronounced when things are moving. You tend to notice when things aren't right because you're hardwired to expect how things will fall for the physics and how people move in real life, and you notice when it's not right. So, what does that mean for Hitman itself? First thing they did, as well as the normal graphic settings, they added an extra option for simulation quality, which actually encapsulates a whole range of things within the game. The basic setting was just for a normal 4-core PC, and the settings by default ramp up as you have more cores available. But you can adjust them anyway, just like any other graphic setting. Nothing's hardwired. This is what it looks like. That setting will affect the audio, the animation systems, the physics, the crowd, and a few little bits in the rendering as well. All coming down to this uncanny valley and trying to actually increase the realism and how you interact with the world. Yeah. One last video in my section. This is the default settings on the left, and the higher end quality settings on the right. This is the Miami racetrack. And no audio on this one. On the slowdown, you can see there's better physics going on the right. And the other one that I'm going to mention in a little while as we go through the talk. If you look in the background, on the right-hand side, we've got crowd. We've got a stadium with crowd that are all interacting when the actual crash happens. So, what sort of things were we changing to do that? I won't dive too much into the crowd. There's a really detailed talk that a guy called Casper gave from I/O about, I think it was 2013 at GDC, and I've put the link on the bottom there. And he was talking about Hitman Absolution, and he talked about the crowd system there. A couple of things that have changed between the two. In Absolution, they had maybe 12,000 characters at any one time. And the levels were designed so they'd stream in and out. So as you moved from one location into another, the crowd would be removed, and they didn't have to run the AI for everything that was in the entire level. Hitman 2, especially because of these things like the picture-in-picture, that's no longer possible. So they've got nearly 2,000 characters, but that has to be spread across the entire level at any one time. And of course, the crowd itself is more intelligent. It affects how you can hide in it. And as I say, the AI has to be simulated even when they're off screen. So, the crowd is a nice one for like multi-core because of the fact the system itself is already very well threaded. Two different areas. There's the simulation. That's the AI, the pathfinding for the crowd, the sort of like their high-level goals. What are we supposed to be doing? That thread, that's on the left-hand side. It doesn't take too much time, but it's done at every single frame. The other area of the crowd simulation is the animation itself. Now, with 2,000 characters, maybe 700 plus on screen at any one time, they can't physically animate all of them every single frame, so it's time sliced. So the more cores you've got, obviously the more time you can spend on actually doing that work. So it spreads very evenly across. It's like an embarrassingly parallel job. But it means the crowd can animate further into the distance, which picks up on that uncanny valley. You tend to notice if people aren't behaving correctly in the distance, but as you go up the higher quality settings, they do. The other one that is detailed in Casper's talk, but plays a part here of scaling on multi-core, is the fact Hitman has the concept of possessing crowd members. The crowd AI is fairly simplistic. It deals with the very top-level things they want to do in the game. It's the crowd watching an event. Are they running away? That type of thing. But of course, you need more than that. If you want the person to feel like they're actually in a crowd, if someone walks through everyone, we'd expect you guys at the front to part if I tried to walk through there. So they need to do that. That's not part of the high-level crowd AI. What they do is they possess individual people. So you've got the idea that the crowd is one AI system, the NPCs are another. They have ghost NPCs. At any time they'll look at the NPCs that are near Agent 47, and they'll possess a few of them. And they'll then start running high-level intelligence, just the same as another NPC from the game. That intelligence allows for things like scripting. So the game designers can actually have people like talking on the phone, people sitting down on a bench, waving flags in the crowd. And of course, by default, they possess 30 people at a time, which gives you a reasonable number in the area that you expect to see, not fairly close to you. On a higher-end PC, you can triple that all the way up to 90. That means 90 unique characters within the crowd system. So that's nearly 1 in 10. And that makes such a difference to actually breaking the monotony within the crowd and making everything feel very realistic. The other one, which is the thing that came out in the video for the Miami racetrack, the level designers had constraints. They would like to populate a level with like thousands of, hundreds of thousands of people if they could, but it's simply not possible. They've got a budget of about 2,000. So one of the things they did is they concentrate the crowd in areas where you'd expect Agent 47 to be moving. But that means the areas where he can't directly get to, but you can still see when you're standing in a stadium looking out across the racetrack, they had to think of inventive ways to make sure they didn't need too many people in those areas of the stadium. So they did things like putting like glass panels on the side so you can't see there's no one behind them. But of course, on a higher NPC, the artist can actually literally swap out the stadium and put in another part of the stands and put people in it. It doesn't affect the gameplay directly, but indirectly it adds to the experience, because if you create an accident on the racetrack, if you shoot the car or if you've planted a booby trap or something, the car crashes, all those people that you can see on the other side of the racetrack will respond to it. So you'll see them panic just like we did in the earlier screenshot. So it makes quite a significant difference when they can do things like that. It adds to that immersive feel for the game. So, what else have we got? Rendering. That's the other ones I need to touch. Obviously, at the moment, Hitman runs DirectX 11. DirectX is a fairly serial API for graphics commands, as people know. But it doesn't mean that all the rendering in the game has to be serial. Things like the scene traversal is very well threaded. They're the yellow blocks in here. In addition to that, one of the things we added that I talk about in the next 2 or 3 slides is visibility culling using a software engine. So that's in addition to the normal Frustum visibility culling. We actually render a simple depth buffer and do occlusion culling using that. That threads very well. I'll cover that in the next few slides. Obviously, we still have the high CPU load on the render thread, which is usually one of the bottlenecks on DirectX 11. And I know a lot of people have been asking about DirectX 12 for Hitman because it was on the forums. I don't know if it's officially announced, but I was told I'm okay to talk about it. DirectX 12 is coming back to Hitman as of probably the next patch, which should be next week. So that makes a big difference to performance for especially these really heavy intensive levels like Miami, where we have like thousands of crowds being animated. Suddenly, that single draw thread can be split by up to 30 draw calls, so, and created on like 4 or 5 different threads. And you can see the difference it makes in a typical frame. Suddenly, the bottleneck that used to be there has totally gone. So you see quite significant performance gains from that. The software occlusion system. It's actually, originally, I was talking to the developers at I.O., and there was a debate between doing a GPU-based occlusion system and the software. And they experimented with both at the time. It turned out they got very good performance with what was actually a very old piece of code from Intel from about 2013. There's a talk I've linked from GDC there, and the source code's publicly available. It reached the point where they thought, we're actually really happy with the software implementation. It scales well, it even runs on the consoles. We added optimizations from the master occlusion talk I gave last year. Master occlusion is great when you've got artwork that hasn't been shrunk to be in a conservative, but their artists have already done all that work. So we mixed the best parts of both to get the performance we wanted. The talks have generally focused on using software occlusion just for the main scene, but I.O. actually use it for all their shadow cascades as well. That saves quite a significant amount of time on the shadows. They also use that simplified geometry they've created for their Z prepass. Rather than rendering an entire scene and all the draw calls and the vertices just to populate the G buffer before the start of the G buffer pass, they just use the simplified geometry. It gets 90% of the work done with only a few thousand, like 15,000 vertices. And of course, it's pretty much stateless, so it's very fast to render. You can see the sort of view that we have here. The top level being a 3D like, non-camera view, the bottom one being the view you would actually see in the game. And that was actually taken from this scene, which is Mumbai. You can see, again, the overlay showing the software occlusion buffer, something around about 320 by just under 200. And on the bottom, you can see their microprofiler, and it's about 5 threads it's using. The numbers and the performance gain we get, this is all after doing all the normal visibility culling, so there's no like fakery going on saying, yeah, we added culling and we saved loads of time. Yes, you're going to save it with frustum culling. This is after the frustum culling had been done. So after normal frustum culling, they had 5,500 draw calls, nearly 13,000 instanced objects being drawn in the world. By doing the software visibility culling in addition to that, they could save nearly 700 draw calls and nearly 4,000 draw instances. Yes, the occlusion cost probably just under a millisecond on what was actually quite an old PC that I was testing on at the time. But it saved nearly 10% of the frame time, even on a very high-end GPU. So it isn't a case of, yes, this works when you've got a very slow GPU, and you're balancing that off on the CPU to save it. This was a good 10% saving, even on a top-end GPU. Most of the savings come from the vertex. You can see that it draws nearly 30% less geometry than it would previously have to. Doesn't make a big difference to the pixel shader. That's mostly because the things you were culling are the ones in the distance anyway, so they don't contribute too many pixels. But it's still time you're saving on the vertices and on this submission to the draw call, to the D3D API. And the last one that I have is the audio. And I'll let this play as I talk through it. Base audio just took the actual, we're going to apply the reverb based on where Agent 47 is standing. So when he's inside the room, you hear all the vibrations. With reverb on the higher end systems, it suddenly starts going, okay, well, let's figure out where Agent 47 is standing and where the audio is actually being triggered from. And depending on how many cores you've got, it has different amounts of mixing buses to actually figure out the best way it can apply the reverb. So it becomes significantly more realistic. They use WIs, and the latest versions of WIs plug into the game's internal tasking system. So it works quite nicely. And they're the main things that are all in the game today. And at that point, I'm going to hand it over to James to talk about the physics. And I'm pretty much on time.
Well, that's good.
It's a miracle.
Hi, guys. Yeah, thanks for coming today. My name's James Van Gogh Brown. I work for I.O. Interactive. And for the last about a year, I think, or so, I've been working on a destruction system for our physics engine. So I'm going to do a bit of a kind of deep dive into that and what it is. So first though, I'm going to show you a little demo of what it can do. Don't worry, there's programmer art coming later that you can see. This is actually going to look good. So. Cool. So first, I should start. Oh, thank you. So first, I should probably start off by saying why we actually want a destruction system in Hitman. And I think really like the first point on here is kind of obvious. It's fun. Like, it's objectively fun, wandering around and smashing stuff up, in my opinion. So this is really what we want to do in Hitman. We want to make a really fun, immersive experience for our players. And adding destruction so that, you know, when you throw something at someone and it smashes into a load of pieces and they fall over and get knocked out, rather than it just bounces off their head. It's much more immersive, it's much more interesting for our players. It means that by doing that, we can also add much more immersive opportunities for things like accidents. So, you know, you can make a chandelier fall down and it will smash into a lot of pieces. It will feel very realistic, even though you're nowhere to be seen. And we can also have way more iconic, big moments in the game. So you noticed earlier the car crash that we have in Miami. That wouldn't be possible without a destruction system. And it, you know, having that kind of dynamic play is really cool. It's really fun. So we start thinking about like what we actually need to build a destruction system. So we do have one in Hitman 1. So for Hitman 2, we really wanted to make an improvement on this. Some of the learnings that we've got over the years of making Hitman games is that we need very specific destruction patterns. So we need to be able to make sure that when something breaks, I don't know, like a statue, for example, or something like that, then maybe the head will always fall off and it will, you know, roll down the hill so it looks cool. We need to make sure that we can like animate destructible objects. So for example, the car driving around the track, it needs to be an animated physics object, but as soon as it gets interacted with and crashes, it has to look completely realistic, like it's just, you know, crashed into a wall. And we need to make sure it scales well for these kind of iconic moments that we have in the game. And as I mentioned with Hitman 1, having an existing system, we don't want to have to rebuild all the assets. We have a single executable at the moment with Hitman 1 and 2 where you can, if you buy Hitman 2, you can actually use a lot of the, so you can play all of the levels from Hitman 1. We have that as a package, and it works in the same executable. So we need to make sure that all those assets can be upgraded easily. So with that in mind, we started kind of looking into, right, do we want to go dynamic or do we want to go predefined? Now, they both have big pros and cons to them. In Hitman 1, we went with the predefined route, which is essentially, in fact, I should explain, dynamic is when you shoot an object and you actually, if you take some destruction, you are dynamically cutting the meshes at runtime. So you're creating new geometry at runtime. Predefined is where an artist has gone in and they've done that cutting for you. So they've removed a lot of the edge cases and things that come from this. It's difficult to have these kind of very specific destruction patterns with dynamic without a lot of tooling support. And the predefined side, it's pretty scalable. You know what you're working with. So we did decide to go down the predefined route, made it a lot easier to work with our original assets from Hitman 1. So I'm going to talk now a little bit about how we actually did this and what the runtime is and how the assets work and all this kind of stuff. But first, I should really give you a little overview of some of the kind of gameplay considerations that we had to make when creating a destruction system. So you can see we've split it into about 2 categories roughly. So we've got the kind of gameplay affecting category, which is anything where it has a significant impact on gameplay. So for example, you can see in the picture, those chandeliers up there, when they fall on the floor, that could fall on top of someone and it could take them out. And it should persist when you come back into the game. AI is going to have reacted to it. People are going to have been like walking around it. You're going to have changed the nav path, all that kind of stuff. So it's significantly impacted the feel of the game. The other side is the cosmetic kind of destruction. So we have, you can see for an example of this in that picture would be some of those lights that are just on the wall. It kind of doesn't really matter if they've been smashed, and when you come back, you can't see all the pieces on the floor. It doesn't really have a huge impact on the gameplay. I mean, it might do, but probably not. So it's a very loose kind of differentiation between the two things. But this is really, you know, it goes into a lot of the design in the level. So we kind of need to think about this. It's a really big topic, and it's not really the full discussion that I'm going to have now, but if you want to talk about it afterwards, we can. So internally, we had to come up with some kind of description of destruction so that we can talk about this in a, in a kind of consistent way internally. So we came up with these kind of 3 object types. So we have the destruction system, which is responsible for controlling the destruction of a specific asset. So every time you drop something into the world that can break, a vase, a window, whatever, it's a destruction system. That's what we call it. So internally within a destruction system, it will be in charge of kind of 1 or more destructible objects. And these are physics objects, basically. So those are the simulated pieces of a destruction system. The destructible piece is inside a destruction object. So a destructible object is made up of 1 or more pieces. So that's kind of the terminology behind it. The other part of the terminology is the phases of destruction that we came up with. So we have 3 real phases. We've got the fracturing, the detachment, and the destroying phase. So the asset that you can see there is made up of multiple layers of destruction. So I'm going to show you in a second what fracturing looks like. The first, so fracturing is basically where you take an asset and you replace it with a number of smaller pieces. So it's still a single physics object, but it's made up with multiple pieces. So when I shoot here with the debug tool, you can see the top level is made up of 4 pieces, and each sub-level is actually made up of a number of smaller pieces. So as I start shooting it, you can see it's fracturing more. The bits that are red or green, that kind of implies that those have been detached. So they've actually become their own object. And when pieces become detached, you can end up with more, you can clump them together. So it's not like 1 piece equals 1 destructible object. You can have a number of them that come off. And then obviously the final stage is destroying. It's where a piece has taken enough damage that it gets removed from the world. So talking about the runtime and how we've set that up, we've got really like 2 main classes of system within the destruction system. We have the instanced subsystems. So every single destruction system in the world will have a number of subsystems responsible for controlling specific aspect destruction on that object. We then have the global systems where every destructible system in the world is able to talk to, and those handle some of the like high-level things in the world. It runs alongside our physics engine as a plugin, so we've made 0 changes to our physics engine to make this work. It just uses the kind of APIs that we have. And we've tried to make a conscious effort to make it as configurable as possible for our designers to use. So just a quick overview. I'm going to go into all this in a bit more detail. But we have a destructible system. It has a kind of configuration layer, which is basically the bit that lets designers go in and tweak properties and values on that system, listen to events, that kind of stuff. Underneath that, we have kind of 3 main categories of subsystem: the visual, the simulation, and the data area. Visual, I'm not going to talk about too much. It's to do with rendering. The animator will like synchronize positions of destruction objects with their visual counterparts. The effect handler will play effects. But really, I'm going to talk in more detail now about the kind of the simulation and the data. But first, I'll just quickly show you this as well, which is the global systems that we have that I mentioned. So I'm going to talk about all of these more later, but just so that you can see that those are there: the insertion queue, reusable memory buffer manager, the system caretaker, and the effects manager. So first bit for a destructible system is how do we store the data in here? So each system has a thing called a registry in it. Now, the registry contains all of the physics objects that are part of a destructible system. So it's all the active physics objects that have been removed, along with the pieces that are inside those physics objects. It's kind of stored in the registry so that we can get this link back to any configuration data that might be part of those physics objects. The other place that we store data is the runtime state. Now, the runtime state is basically all the changes to a destruction system that since it's been initialized. So the idea is that from the runtime state, we just have to serialize that. And when we want to load back in a destructible object, we should be able to rebuild the whole thing from the runtime state. So it includes things like, if you've got connected pieces and stuff like that, it's the connections that have been broken, or it's the amount of damage that's been applied to a piece, that kind of stuff. So that's where the data is stored. So on to actually how we use it. First off, I'm just going to highlight this. This is called the activator. It's one of the subsystems within an instance. Its responsibility is to essentially figure out when something should be updated. So a destructible system should only be updated occasionally, maybe. But you can see in here, this is a real level that has 16,500 destructible objects in it. Only 11 or 12 of them are ticking at the moment, are being updated. There's no point in updating everything. So this actually gives us a really quite big performance improvement, and it ties into external kind of stimuli within the level to make sure that we know when this stuff should actually be updated. The actual beginning of the destruction pipeline, however, it begins with the interaction handler. So every destructible system has an interaction handler that plugs in to external gameplay ideas, as it were. So shots, explosions, collisions, that kind of stuff. Its responsibility is to take all of these external events that can cause destruction and kind of convert them into a uniform destructible force that can then be acted on. And then it passes it on to the interaction processor, which is next, the interaction processor. It stores a queue of these interactions, and then it processes them each frame. So its responsibility is to essentially take each interaction, propagate the damage through the physics objects that that interaction was applied to, figure out what the state changes are from this propagation, i.e. fractured, detached, destroyed. What do I need to do to this physics object? Do I need to create new physics objects? And then it will apply those changes. It's also responsible for ensuring that at the end of a frame, everyone knows what's happened. So effect systems, things like that, may need to play effects when this kind of stuff goes on. So this is responsible for saying, hey, I just detached this piece or broke this piece so that we can play the appropriate things. So the actual damage propagation part is, it's fairly straightforward, but basically what we do, a force comes into a physics object. We do some initial kind of filtering just to see, does this force actually, is it high enough to do anything? We then find all the pieces within that destructible object that might actually be affected. We then can go through each individual piece and apply an extra level of filtering. So it might be that a piece is extremely strong, and so, because it's been set up to kind of look like steel or something like that. And so then we just don't, we might not want to apply any force to that, or it might be the opposite. It's glass, so it should break, or something like that. We then pass that information into the piece, and we figure out what the state change of this piece is going to be. Should it be detached? Should it be fractured? After this, we then reduce the force down a little bit, and we pass, and that's also configurable. I'm going to talk about how later, but we reduce down the force based on how much damage might have been absorbed by that piece, and we pass it on to all of the pieces that are directly connected to it. This is iteratively done. So at some point, you're either going to run out of force, or all the pieces are going to have been visited or destroyed or whatever. So once we've got this, we know what the state change is going to be from this force that's been applied. So we then perform some kind of island detection, which I'm going to talk about on the next slide. Final results get returned back, and then you can apply them and actually do the state change. So I'll talk about island detection that I mentioned just now. This video will explain it way better than I will, but basically it's when you interact with a piece, and you can see that that's formed this island at the top, and it's because I haven't really directly interacted with any of those pieces, right? So this is what you expect to happen. So the way that we approach this is with an algorithm that's essentially a flood fill algorithm, right? So you have a piece that gets removed from a destructible object, and you find all the candidates. And a candidate is a piece that's connected directly to that removed piece. So in this video, you can see it's that blue piece is being removed, and all the pieces directly connected to it get stuck in a list. We just apply a group ID to the first piece in the list, and then we recurse through all of its connections and apply the same group ID. We then go to the next piece in the list. Has it been visited yet? Yes, it has. Fine. If it hasn't, then we recurse through that. So at the end, you're going to be left with everything will have a group ID that just increments. So if it's in the same group, it means there is an indirect or direct connection to it. And if it's not, then it means that it's an island. So we take the smallest group of islands and we remove them from the main piece. So that basically means that you end up getting additional physics objects being created indirectly from a force being propagated. So that's kind of how we try and deal with island detection. It works pretty well. So I'll just move on to the global systems and how these work and how we can modify the world. We have a thing called the insertion queue. So the first thing that a physics object can do when it wants to be stuck into the world is it gets a request into the insertion queue. And the insertion queue is responsible for basically just putting stuff in the world. So we don't want in one frame to have 10,000 objects stuck in the world because it's going to chug. So instead, we throttle this based on the amount of things that are going on at the moment. We make sure that we haven't got too much going in. We also have the ability to drop requests. So if there is a piece that's kind of marked as not particularly important, but it would be nice to have, and there's loads going on and you can't really process all these requests right now, we can just kill it and tell the guy who asked for it, the system that asked for it, no, we can't have it. And it will actually just upgrade to downgrade, whichever way you look at it, to a destroyed event instead. So the thing will be marked as destroyed, and then it will play an effect for it. The other thing we have is an effects manager, which is responsible for playing the various effects, so user can actually see what's going on. We have 4 main effects. Fractured, detached, destroyed is fairly self-explanatory, I hope, by this point. Collided is basically when a piece collides with something, maybe nothing really happens to it apart from some damage is applied. So you might have something that smacks into a wall and it's been damaged a bit, but we just want to play some kind of brick dust or particle effect or whatever. So that's what that's for. It also pulls effects together to make sure that we don't end up spawning a ton of new effects and that kind of stuff. So the other side is how we manage resources. We have 2 kind of main systems for this. We have the reusable memory buffer manager. This is responsible for maintaining memory buffers that you can just reuse and reuse across different threads when you're doing damage propagation and that kind of stuff. And this vastly reduces the overhead of allocations and freeing. So, I mean, it's a very, very useful tool to have. The other side is the system caretaker, which is responsible for kind of aggressively trying to reclaim memory. So in this example, you can see there's a load of pieces on the floor there, and they don't really matter because they're not being marked by the designer to matter so much. So when Hitman looks away from them, this has been set up to be very aggressive. But when Hitman looks away, it will remove them from the world, and it will make sure that any memory that they're using is being freed and it can be reused elsewhere. We also make sure that destructible effects and things like that, the various pools that I spoke about before, they get reduced, and we can kind of free up the memory and reclaim memory from that. And it also attempts to try and make sure that physics objects that haven't really been interacted with for a bit, we sort of force them to sleep so that they don't get simulated anymore as quickly as we possibly can. So that's really what the caretaker's for. So now we've got all that, how do designers actually work with this? How do they make destructible objects? So the first thing that we've got is a proprietary tool written in 3ds Max. Now, this allows designers to quickly fracture stuff using Voronoi fracturing, but they can actually fracture it in whatever way they want. We've just supplied this to them. The other thing that it's responsible for doing is helping us automatically generate physics shapes based on the geometry that's there, that maintains convexity or tries to ensure that you've got the smallest primitive that you can, so a box or a sphere or whatever that fits within that shape. It also is responsible for allowing designers to control the hierarchy so that you can actually define the fracture level. So you can have your top level object. When you fracture it, this will make sure those objects get put down, as kind of children of that object, so that you know that it's what it's going to fracture down to. And that's a recursive process. I think at the moment we're limited in a single system to a few thousand bones, a few thousand objects. So. The other thing that we have, that designers have in their toolbox, is the destruction materials. So I touched on this before during damage propagation, but what this allows designers to do is control how specific pieces within a system are going to react to damage. So we have two kind of main areas of this. There's the strength and the shock absorption area. So the strength is responsible for saying, how resistant am I to damage? And incidentally, there's a number of parameters under these two kind of categories. It's not just two. But the strength is, how resistant am I to damage? As I get more damage, how resistant am I to damage? So how weak do I become, and that kind of thing. The shock absorption is how much damage do I absorb when I'm doing damage propagation into the rest of the system. So the nice thing about this is that designers and artists can create a single destructible system which consists of glass, concrete, and wood or whatever. So they create these materials that can be reused across different systems to try and tweak the way that it's going to behave. So with the whole connections thing I was talking about, we give some control to the designers, but we've tried to automate connection creation as much as possible. So connections, as I mentioned before, it's kind of, what pieces am I directly connected to that are near me? So we do this by inspecting the geometry and seeing what geometry is kind of near to other geometry, and then we stick a connection in. And it works very well, and then we basically allow designers to decide when things shouldn't be connected, because the common case is that they are connected if they're touching, and then we just allow designers to kind of turn it off. So it means there's a way less overhead for them. Another additional kind of attribute that you can add to objects is the anchor attribute. So in this video, you can see these doors don't have anchors on them, and the problem is that as soon as Hitman shuts the door, all the glass falls out. So anchors are a way of saying when the animation of this system is done, if any pieces are connected to an anchor piece, that anchor piece goes with the animation. So it's basically just a way of us being able to animate objects and still maintain this kind of realistic feel. So we have a few piece attributes as well. So there's two main ones. There's remain and orphaned. There are a couple of others, but the remain could probably also be called important. And basically what this does allows a designer to say, this piece should never be removed from the world. It can participate in damage propagation and all the rest of it, but it should be there forever. You can never destroy it. So in the example you see there, that's a statue that's been pushed on top of one of the targets. And this is an example of something that should stay. So when I save and I load, or if I continue shooting this statue, I imagine that it's always going to be there because it's a set piece and it reminds the player that something big has happened in this area. And it's actually changed the state of the AI in that area and that kind of stuff. Another attribute is the orphaned attribute, which is basically a way of saying this piece should never have any connections attached to it. So it means that when a piece fractures, that piece that's an orphan, as it were, is just going to fall off immediately. And we found some use cases for that are really, really useful. So yeah, that's why that's there. So this is all the ways that the designers can actually get this stuff into the game. So how they actually work with it is they go into the 3ds Max tool and they set everything up as you expect. We then export to our own kind of proprietary format that we have internally. And then there is a thing on every user of our engine's machine called the resource server. And the resource server is configured to look at a folder where all of our assets are, read an asset, and basically turn that asset into another kind of asset. And it's not a one-to-one mapping, it's a one-to-many mapping. So from one asset, you can extract a number of different assets. So the way that we do this is we call it packing internally, and you write yourself a packer for the resource server. So I've written one for the destruction system, which basically reads all of the geometry and the various attributes, and it turns that into a destructible asset that gets stuck into the disk. It contains all the connection map information and all the other stuff that you would expect. Then what can happen is that's going to show up inside our editor, and a designer can drop an instance of that into the world. So when the designer or artist, whoever, goes back into 3ds Max and makes changes and they re-export, it's going to go onto the disk. The resource server will pick that up. It will repack it. It will update the destructible asset with the new changes, and then you'll see automagically that it's all updated in the editor. So that's basically the pipeline that our designers and artists work with, and it works very, very nicely for them. We've had no complaints, well, some, but it's cool. So yeah, that's really it from me. So I'm going to hand back to Lee now, who's going to give you a kind of conclusion. So here you go, Lee.
All right. Thank you, everyone. I see everyone's managed to stay through pretty much the whole talk, and no phones have gone off, so success. Right, the conclusions then. There's one thing I'll say that going off script, just as an explanation, we realised we probably should have put a slide in for it. The way the Hitman levels are designed themselves, they have a concept of like layers and bricks. I don't know if that's a Lego reference coming from Denmark and that, but the idea was like most of the levels share common layers, and then for DLCs and that, IO might create an extra layer for something like Halloween for a particular mission. And that's one of the features they use for adding all of these new things. When we talk about Miami with extra crowds added in certain stadiums, and the stuff James has mentioned where the physics, the level designers could go away and play with the physics, they could just create a new layer for the high end with just some extra things changed. It could be the remain flag, so things that would vanish on a low-end PC might remain longer on a high-end PC. Things like that. So that's just an explanation of how they layered up the game to make use of these features so the level designers could actually decide, low-end system, this is what experience we want the user to have, and this is what's important for us to add as they get some spare power. Anyway, the conclusion for everything. Going right the way back to the concept I mentioned in the Uncanny Valley. Really, what we wanted to get across in this talk is that realism for the game is about far more than just the pixel quality. It's incredibly important, and there's so many things happening in graphics, and plenty of talks at GDC on those. We wanted to emphasize the other things, whether it's the animations, the physics, it's the things that make the world feel unique. And yes, make use of it as CPU power increases. There's been quite a significant change over the last few years. Please make use of it. It does have gameplay implications, but with careful consideration, that's not always a bad thing. Even graphics have gameplay implications. You add shadows to a game, that changes the keys to what's happening behind you. You add reflections. That makes a huge difference, especially if you're trying to sneak up on someone. And I believe in Hitman 2, the AI actually sees into the reflections, things like that. So all these things have implications. Just because you're changing something on the CPU doesn't make it any different. So that's really good. And especially a sandbox game, these little things add playability and replayability maybe is a word for it, to make the user come back and have another go. As James says, at the high end, it's these accidental things the user creates that they have in their memory. It's what makes them come back to a franchise later on. And the other thing, the audio it's only got a couple of slides in here. I know the guy who did the audio is writing a white paper on it, but it really does add a lot of immersion, and there's quite a few nice audio systems going around today. A lot of them were done with VR in mind, for, to actually add that level of realism, make use of it even in normal games. So I think we've covered more or less everything. I think we might do the draw before we take the questions, so then we don't have to worry too much. How do you want to do the draw? Have you got tickets? Then if anyone's in a real rush to get out, at least they can. You haven't been deprived of it, so I'll tell you what, do you want to do a pull?
Sure. Sorry to the losers, I apologise. There you go.
Okay then, let's see. This says, I'll do all 6 digits. 1, 3, 4, 2, 5, 7. So, 4, 2, 5, 7. I still can't see up here. Anyone got that one?
Oh, wow. Yeah.
Say no. 4, 2, 5, 7. Anyone? Let's do another one. Go on.
This one. Here you go.
Typical. Right, there we go. Okay then. 4, 3, 2, 3. Has someone given me the tickets from the last room?
Oh, down here.
Oh, we got someone?
Yeah.
Yay. There you go then. Okay, so let's do the questions then. We've got just under 10 minutes. So we're both up here for these.
Where's the microphone?
Do you want people to go to the microphone if they're asking questions? Is that the idea? Yes. Yes, okay. Cool.
Ooh. No questions.
Maybe I should have held off on the raffle till after you ask your questions. Typical. That's why you were here, I know.
I actually do have a question, but it's crowded around here.
All right.
Cool.
Okay, so you guys mentioned that the quality setting touches a lot of stuff on your simulation side, right?
Yes.
I assume that this stuff cannot have any long-term gameplay effect, because if it does, how do you deal with saving and loading and synchronized states of those settings being different? I mean, situation with the crowd, right? I assume when the car crashes into the crowd on the best simulation settings, the crowd runs away. What happens if I load the game on the low simulation settings where that scene looks completely different? There is no crowd there in the first place. So how do you deal with those conflicts, right? Because you're going to end up with them one way or another. Someone saved the game on the best quality settings, and the scene hot crowd ran away. Someone loads on the low. What's happening then?
I think the way that it's really dealt with it, and James touched on it a little bit, some key features do get saved out. So, like if they see something as being important on a higher level, the level designers can say we want to save out these physics events. Obviously, if you load on a lower quality setting later on, then that stadium doesn't exist. But then it just puts in the old stadium. Where the people would be exactly will have changed. If you load the game anyway, you wouldn't expect every single person's location to have been saved perfectly. So there's a few things. James, do you want to add something?
Yeah, it's a really great question actually. So we always try to make sure that when we're doing the level design, and we know that we're going to be having to produce a sort of best quality, higher fidelity experience, that there's always a kind of migration path between the gameplay stuff. So you're always going to make sure that you've got the same kind of gameplay concepts in the area. It's just that when you're there, it might feel way more immersive if you're on the kind of best platform. So it's never going to actually change the gameplay, fundamental ideas behind it, but it will change the experience.
Okay, thank you for that.
Yeah, no worries.
I mean, the important thing, like that stadium we showed you, Agent 47 can't enter that stadium anyway. It's a visual thing that you see in the distance, but it's not like, if that crowd does something, it's changed you when you go back, because you can't get to them. It's just a visual.
Yeah.
Yes, next one.
Yes, I have a question about how to store data between the safes. You mentioned that the destruction pieces that will remain during the save, right? So how do you store the data? You store every piece's location or what?
How we store the data for the destruction system when it's saved?
Yes.
Yeah, so we'll serialize out the runtime state, which is basically the changes from the original configuration that this destruction system was loaded in with, which is static and it doesn't change. And then we will serialize out the transforms as well, along with that. So that becomes part of the runtime state. But basically with that, we can just rebuild it. So we can, because we know what the changes are, so we know that, you know, we have to remove these connections, we have to have these many physics objects and all this kind of stuff. So that's basically how we save and load it.
So you need to simulate the destruction process or just the...
We don't need to simulate the destruction process because essentially, you know, when the destruction process goes on, all it does is create new physics objects, right, that are configured in a certain way. So as long as we've stored the data and we understand how we can reconstruct those physics objects, that's all we need. So they get put into the world and then the simulation continues from where it left off, and, you know, it might be that it's falling or it might be that it's just lying on the floor or whatever. So yeah, that's how we do that. Does that answer your question?
Yes, sir.
Cool.
Thank you.
No worries.
Okay, we've got about 4 minutes, so any other questions? That's someone heading for the mic or they're heading out? Oh, Mike.
Can you tell us a bit more about how the destruction system works on top of the underlying rigid body simulation?
Yes.
How do you go on from the simulation?
Yeah.
How do you detect what's going to be destructed? And all of that?
Yeah, sure. So the rigid bodies are obviously going to be configured to have a number of different a number of different shapes that make that rigid body up, and those are the things that are going to sit in the broad phase, and you know, they're the things that are going to actually be the physics object in the world. So each destructible object is essentially just a rigid body, and then it's configured with a number of shapes. So the API that we require for the destruction system to work is that we can create rigid bodies, we can dynamically add and remove shapes from those rigid bodies, and that's basically it. The rest of it is all taken care of because it's simulating within a physics environment. So yeah, does that answer your question?
Yeah, so do you do detection between collide and solve, or do you take destruction after solve? Because they both have some implications.
So we take it after solve. It's something that we're actually going to be trying to investigate soon to try and figure out, because there's certain problems with that. You know, you end up needing to be able to maintain momentum and stuff like that. I mean, in the use cases we've had, it's been absolutely fine. But moving on, there are definitely situations where we need to be able to take it earlier. So yeah, we're investigating that at the moment. Cool, no worries.
Okay, any other questions? Okay then, thank you all.
Thank you.